Alright, silly people, here's the situation. We're going to be proving a uncertainty principle, just going from this general result for uncertainties of operators, general operators A and B. Particularly, we want the one for x and a Hamiltonian. So the uncertainty of position times the uncertainty of energy, both squared, of course. So we're just plugging those into here and seeing what we get. So I'll go ahead and expand what the general Hamiltonian is in here. It's a momentum squared divided by 2m plus a potential inside this expectation value. So we can simplify this commutator quite a bit. First of all, by just splitting it into a commutator of x with p squared over 2m plus a commutator of x with v. Now the potential is usually just a scalar function of position, and so it commutes with position anyway, so we can cancel that guy out. And then after that, we can factor out the 1 over 2m from the leftover commutator. So it's 1 over 2m times the commutator of x with p squared, which we can almost work with. So I'm going to pull out the 1 over 2m from the expectation value as well. So we'll have a 1 over 4im here times the expectation value of, and then this commutator rule, I haven't really discussed it in relation to Griffiths yet, but there is a general commutation rule that says A with BC is equal to A with B times C plus B times A with C, right? But B times C here is just P squared. So we've got the commutator X with P times P plus P times the commutator of X with P. Now both of the leftover commutators are just the general commutation relation as well. So we know what the result of that is. It's I h bar for both of them. So this is I h bar p plus p I h bar. Those two will add up and create the expectation value of 2 I h bar p. So we get some cancellation. The I cancels out this I. A factor of 2 is canceled out. We could move the h bar out of the expectation value since it's just a number, so it's just h bar over 2m times the expectation value of p. And then we can take the square root of both sides of the inequality here. So sigma x, sigma h will be greater than h bar over 2m, and then when we take the square root, we have to specify that this is now a magnitude of the expectation value of momentum. So that's the thing that we were trying to get to in the proof. Then Griffiths asks the question, why isn't this incredibly useful for stationary states? Well, the hint is in the name. Stationary states imply that the object is not moving. So generally, this is also in his little blurb about stationary states, that the expectation value of p in those are always 0. So yeah, if you know that sigma x, sigma h is greater than or equal to 0, you're not really getting a whole lot of information out of that. So yeah. Alright.